All right, we are on our third video of Chapter 16. We've been looking at some of the energies involved in nuclear reactions, how they release a lot of energy, and how to do that type of stuff. We're going to look at more specifically in this one at radioactive decay and the different or various forms of radioactive decay. And then in doing so, we'll look at balancing some nuclear reactions as well. So a little different than balancing chemical reactions. Let's get going. In order to start, we need to look at subatomic particles, and some of this should be a review for you, especially when you see proton, neutron, and electron. So let's just write what the symbols are for these subatomic particles. So the first one is a proton, okay? We could draw this, okay, as a P, which is oftentimes what we see, and we put a 1 and a 1 here on the top and the bottom. So the mass number up top, proton has a mass number of 1, and the atomic number on the bottom, proton has atomic number of 1 as well. You could also do, this is a hydrogen nucleus, okay, so when you have 1 proton, mass number also 1 there. So you could do either of these symbols for a proton. All right, neutron, okay, also has a mass number of 1, and we usually give it the symbol N. So it has a 1 here for the mass, and then the atomic number, that's the number of protons. The neutron has 0 protons, so we're going to put a 0 there. Now the electron is another one that we should be familiar with, and we're going to give it the symbol E. Now an electron has not a mass number. It does not. Mass number, remember, is protons and neutrons. Okay, so electrons do have some mass, but it's usually so small we sometimes ignore it compared to the neutrons and protons. I'm going to put a 0 here. And then this is opposite in charge to a proton, okay, so we're going to put a -1 here. Now, another way of writing this, and we're going to see this come up, so this is a little different. So I'm going to say, or you could also write this electron with a B, okay, as a beta particle, and the same symbols, the 0 and the -1. Now this is, we call this a beta particle. And this is identical to an electron, but it's just if this electron comes from the nucleus, we call it a beta particle. We'll get into that more, but let me just write identical to normal electron. But comes from the nucleus. All right, we'll identify that a little bit more. Now the next two, at least this next one especially, positron is not one we've talked about when we talked about subatomic particles way back when we were looking at protons, neutrons, and electrons and how they make up the different elements. So a positron, I'm going to give the symbol an E for the symbol, and it also has 0 here for the mass number, but now for the atomic number, this is going to be a +1. Now, we could also, if we are going to use the beta thing, we can also say or, call it a beta with a 0 and a +1. Now, what does this mean? Is this a proton? No, it's not a proton because you can see that the mass is not like the proton. So this is just like an electron as far as mass goes. So same mass as an electron, but it has the opposite charge of an electron. So an electron we usually say is a -1. This has a +1 charge. So same mass as an electron. So it's not a proton, but it has the same charge as a proton. So we'll look at those more later and how these particles even come about. So don't worry, just want to kind of identify these so far. We've talked a little bit when we talked about Rutherford and his gold foil experiment way back a while ago about alpha particles. So just to kind of remind yourself of that, alpha has a symbol here, so you can call it an alpha particle like this, and it has a mass number of 4, atomic number of 2, or you could also write it as He, since when you have 2 protons in the nucleus, this is the nucleus of a helium, and so you could write it either way. All right, so these are the different subatomic particles Now we're going to get in a little bit more and talk about some of the decay types. All right, so here's a list of the 5 different types of decay that we'll be looking at. Okay, so we're going to identify them and be able to write these reactions. As we're going through them, we will be writing the nuclear equations for each of these types. So just a couple things. These are different than balancing a chemical equation where you have the atoms balanced on both sides of the reaction. We might not be balancing atoms here, but what we do have to balance is both the mass number and the atomic number. So we'll get into some practice of that. Make sure you have a periodic table out because that will be really helpful as well. All right, let's start with alpha particle emission. Alpha particle emission is our first one that we're going to be looking at. And let's get this set to go. That's the one with a helium nucleus. Okay, so you have an initial radioactive isotope. Okay, we call this the parent isotope. Okay, this one is your initial one. And then it goes through some type of a decay. In this case, this is going to release an alpha particle. So you can see here it's coming out. Okay, so this is not very stable. It releases an alpha particle. And what you have then left over, okay, after the alpha particle is left, is now a new isotope. This has a different mass number and it has a different atomic number because we just lost a helium nucleus, basically. And we call this the daughter isotope. All right, so the reactant one would be called the parent, and then the product is the daughter. Let's just do a practice here. And we're going to do this with uranium-238. So it's a specific isotope of uranium with a mass number of 238. So I'll give it the symbol U. 238 for the mass number. On your periodic table, you should be able to tell me the atomic number. And I have 92 there. Now, this is going to undergo a decay, and we are told it will undergo an alpha particle emission. So one of the products will be the alpha particle that's released. We know that particle symbol, so we'll draw that here. And then you have to figure out, well, what else is left over? All right, and this is where we want to do the addition and figuring out what's equal on both sides. Now, we're not going to have a uranium anymore because we're going to be losing 2 protons, so it's not uranium. So what you want to do is you want to look at the mass number, okay? So on both sides, that mass number has to be equal to each other. It's 238 over here. And so this has got to be 4 plus something will also equal 238. So what does that have to equal? It's going to be 234. We can do the same thing to the atomic number. I'll switch color to make it a little easier for you. And I wrote a little close there, but you can see here we have a 92. On the bottom here, this also has to equal 92. So we have 2 plus something equals 92. This atomic number, the number of protons, has to stay constant on both sides. We know this has to be 90. All right, so then we can go in and write the symbol. It's going to have the atomic number of 90, the mass number of 234. And now that we have these numbers, go back to your periodic table and tell me what is that? What atom is this? All right, so you're looking up which one has an atomic number of 90, and you see that it has the symbol of TH for thorium. All right, so this is how it goes. You're told what type of particle or decay it goes. This one was alpha. So you put the parent on the left-hand side, and then on the right-hand side, you drew the alpha particle symbol, and then you had to just do a little bit of simple math to make sure that the mass number and the atomic number added up so that you got the same on both sides. Look at the periodic table to figure out that the daughter isotope was thorium-234. All right, so that's one type of decay. The second one that we're going to go after is the beta emission. All right, so here's this beta particle that we need to talk about here. And get this ready to go. This is when you have a neutron in the nucleus and it gets converted to a proton. And in the process of that conversion, an electron leaves, okay, is actually produced. When that neutron converts to a proton, it makes an electron as well, and then the electron leaves. So this is where we're talking about this, an electron that came from the nucleus, even though there's no electrons in the nucleus, right? Those are on the outside. But this one was made when when a beta emission occurs. So just to kind of look at what this looks like, we have a neutron. All right, there's the correct symbol for a neutron. And when this undergoes beta emission or beta decay, it produces a proton. And you can even do our little check here. Right now, the mass number is equal on both sides. So whatever this particle is, it's going to have 0 mass. And we know that the neutron did not contain a proton. And now if we have a proton, we need to have something with opposite in charge of that proton. This is going to be a -1. And this is the electron here, all right, or the beta particle that we can call it. We could also write the same thing. We could do beta 0 -1 and put that in either one of those. All right, so just kind of see this picture here. Here is a neutron. All right, this is a carbon 14 nucleus. It is very rich in neutrons, and if you look at the N to P ratio, remember that, the neutron to proton ratio, for elements under atomic number of 20, this should be right around 1. Well, this is 1.33, so it's higher than 1. Well, so in order to get closer to that 1 ratio, it would need to lose a neutron and maybe gain a proton. So when this does this, this neutron is converted to a proton, and in the process, you have this electron getting ejected out of the nucleus as well. What is left over now is something with the same mass, because going from a neutron to a proton hasn't changed the mass, but we did now have a positive charge, okay, getting produced, and so that negative charge, to balance that out, had to get ejected. If you look at the N to P ratio, the neutrons to protons here, for a nitrogen 14, all right, this is a ratio of 1. So this has now become more stable. It was radioactive, and now it is more non-radioactive. So a lot of the decay will happen in order to become more stable or less radioactive. All right, let's do an example. We have lead 214. Now looking at the periodic table, I can see its atomic number is 82. We are told this undergoes beta particle emission. I know that a beta particle is a 0 electron with a 0 and a -1. This is getting emitted when this lead converts a neutron into a proton. All right, so let's do the math here and figure out, well, we know that this is 214. So 0 plus something has to equal 214. We know it's 214. All right, switching colors. Yeah, we'll go green. We have on the bottom, the atomic number is 82. So we know whatever we have here has to also equal 82. We have a -1 plus what will give us 82? And that is going to be 83. Get your periodic table out, and you will see that the symbol for the element with the atomic number of 83 is bismuth, Bi. All right, so this is now the beta emission. We're going to go do another one. Okay, the third one we're going to look at is called a positron emission. All right, so for this one, you have a positron getting ejected. Let's see if I have this here, from the nucleus. So the positron is what we were looking at earlier. That was one of the new symbols. And this has the same mass as an electron, but it's opposite in charge. Okay, so electron's a -1, a positron is a +1. This occurs when you have a proton, so here's this proton right here, and it's getting converted to a neutron, and in that process, that positron particle is released. Let's see if we can draw that out. So we have a proton getting converted to a neutron, and what's left over? We know it has to have a 0 up here, and it's going to be a +1, and we're going to put an E there, and this is what we call the positron. All right, this is usually if you are neutron poor and you need to get more neutrons, you convert a proton into a neutron. So example of that is that the radioactive isotope of potassium, potassium-40, will undergo positron particle emission. Let's draw that out. We have K, atomic number is 19. That's on the reactant side. And then on the product side, we have the positron being emitted. And what is left? We know that the mass number doesn't change here, and that makes sense. If you have a proton getting converted to a neutron, proton and neutrons have the same mass, so the mass number is the same. However, we have now gone down. If you're losing a positron, you're converting to a neutron, you have gone down an atomic number. So +1 plus 18 will give you that 19. And what is the symbol then? Look on your periodic table. Find the one that has the atomic number of 18, and you get argon. All right, so in all three of these, first three, particles are being released, okay? They're being emitted, okay? All of them have the word emission, so it makes you think that this particle is on the product side. The next one's a little bit different, okay? This is where a particle is getting captured, and it's going to go on the reactant side. So this is number 4. And this is called electron capture. All right, so this now is an electron that's kind of close, the inner shell electrons, all right, so it's close to the nucleus, and it enters the nucleus and gets captured, and this converts and joins with a proton to convert to a neutron. Okay, so overall is you're converting a proton into a neutron. So here's the picture here. Here's this proton. Here is an electron coming in. And then in the end, you have a neutron. Let's see if we can draw this out. So here is the electron plus a proton. And the net result is now you have a neutron. And if you add these up right here, you get 1. And if you add these up right here, -1 plus 1, you get 0. All right, so this now is the particle getting captured, changing a proton to a neutron. Let's do an example here with mercury. 197, atomic number is 80. Now we're going to put the electron that's getting captured on the reactant side, so this is going to get an electron. And let's make sure our mass numbers and atomic numbers add up. Does not have a change in atomic number, that's still 197. And then we have 80 plus -1, that's 79, and you can look and see that that is gold. So the effect of both the electron capture and the positron emission is both are getting converting a proton to a neutron. So this would occur for all of those radioactive isotopes that are lower on the band of stability. It helps them move up higher on that band. All right, looking at the fifth one. So this fifth type of decay is called gamma radiation. A couple things to note here with this one, that this is not a particle at all, okay? So there's no particle, but this is high in energy. So energy is being emitted here. Symbol for gamma kind of looks like this. Kind of draw that maybe better than I can. So since this is not a particle, there is no change in mass or atomic number. That makes balancing it pretty easy. But often this will go along with other radioactive decay. So especially like with an alpha decay, and here's the example here, uranium-238 undergoes alpha decay. We looked at this already. It produces that alpha particle and energy is given off. So it's sometimes added and given off in the process of other types of radiation. All right, let's look then. These things, all right, the whole goal is for radioactive decay is for the radioactive isotope to start decaying until it forms a more stable or non-radioactive isotope. And this often isn't just one step. So I just want to show you kind of the steps involved for uranium-238. And you can see it goes from way up high here with a, overall it has a ton of change, right? Mass number from where it starts way up here to where it ends is way down here. So the mass number overall decayed by 32 and the atomic number decreased by 10, undergoing both beta and alpha decay. So here's an alpha decay, and then a couple of betas, more alpha decays, all the way down. So these are all different radioactive isotopes, which also then start decaying. In the end, it will stop when it hits a non-radioactive isotope. So this is called a series. Since it's not just one step, it just takes many steps for it to get there. Let's see, next thing I want to just show, let's sum it up. Now that we have seen these all, let's make sure we can kind of see how it looks. So here is kind of a summary of those 4 types that emitted a particle and how it changed the isotope itself. So in the yellow, you can see is the middle one. This is where you start with, the parent one. And you can see that the beta emission, okay, now you have gone up in atomic number. So you've kind of gone up 1 on the periodic table. Both the positron and the electron capture have turned a proton into a neutron. One captured an electron to do it, the other one emitted a positron. But the effect is that you've gone, the mass has stayed the same, but you've gone down in atomic number. And then the last one, the alpha particle, you go down in both the mass number and the atomic number. So it's gone down a couple steps there. Keep this picture in mind as you kind of work through these. Let's try an example. All right, so I want you to go and in a couple seconds, we're going to pause this video. I want you to fill in the missing particle. All right, and then also label what type of decay is going to go on when this particle is captured or emitted. So pause, come back. All right, I hope you were able to figure this out as well. The first one was kind of an easier one. It was the only one that was on the left-hand side. All right, so this is the one that was the electron capture. Electron comes in, and you can see that we now have changed. Okay, the atomic number has gone down by 1. We had a neutron, or a proton converted into a neutron. The next one, okay, if you look at how things have changed, here we are emitting a positron, and mass number has stayed the same, and we have decreased in the atomic number. It went from a 29 to a 28. Proton getting changed into a neutron. Next one, you can tell this one pretty easily. This is a large change, okay, a change of 4 here and a change of 2 here in the atomic number. So this was an alpha decay particle. And the last one, you have the beta decay. All right, you can see that the mass number is staying the same, but we have increase in the atomic number. This is when the neutron converts into a proton and it releases an electron. All right, there we go for that. Hopefully you just need some more practice in writing out these particles and the different types of radioactive decay.